Hello everyone, welcome to Dr. Ravi's Academy. In today's virtual class, you will be understanding how to solve a problem on aeroplane, that is gyroscopic couple on aeroplane. So how the gyroscopic couple is going to affect the stability of the aeroplane, so that you will be solving by means of a problem. So let us look at this problem. In this, an aircraft is flying at a 300 km per hour. The velocity is given. It turns towards left. It is negotiating a left turn. In doing so, it completes 1/4 of circle of 80 meters radius. So, as it negotiates a turning, the radius of curvature is given, that is 80 meters. So, 1/4 is irrelevant to our problem. So, 80 meters radius of curvature is required. The mass of the engine and other parts is given, that is 520 kg, and its radius of gyration is given 345 mm, so that you can calculate the mass moment of inertia of the engine. And the engine is running at 2400 rpm. The speed, the velocity, the angular velocity of the engine is also given, and it is said to be clockwise when seen from the rear end, that is back, it is called rear end of aeroplane, and is asking calculate the gyroscopic couple and its effect. So these problems, gyroscopic couple problems, you have to solve in 2 steps. The very first step is you have to draw the schematic diagram of the application. In this problem, it is application is aeroplane. So let us draw the schematic diagram of aeroplane, and then the vector diagram. You have to draw the angular momentum vector diagram. 2 diagrams are required, and the calculation part, you have to calculate the magnitude of the gyroscopic couple as per the given data. So let us start with the schematic diagram. Let me show the aeroplane. So this is the aeroplane, right? And you are going to draw the top view of the aeroplane. So here let us draw the top view of the aeroplane. So it is, I am just approximately I am drawing this. Let us see. This is the nose, and you have tail or rear end axis. Let me represent, and you have propeller here. This is propeller, and this is the nose, that is front end, and this is the tail of the aeroplane as it is moving forward. This is the direction of the motion, and you have, let me complete the diagram. You have even, so this diagram exactly observe, I have drawn this 2 wings and the backside wings, as well as I have represented this also. Now this is the diagram of the aeroplane as it is moving forward. And after drawing this particular diagram, let us understand the given data. An aircraft is flying at a 300 km per hour. The velocity is given, velocity v is equals to, it is 300 km per hour. So convert this into meters per second. It is 300 into kilometer is 1000 meters, and hour is 60 into 60, that is 3600. Now this is in meters per second. So this value is, you are going to get 83.33. So velocity is 83.33 meters per second. That is the given first data, and it turns towards left. Here clearly it is mentioned that the aeroplane is negotiating a left turn. So the left or right turn, remember, it's one very important aspect in the solving the problem. Here with respect to the body of the aeroplane, this is the left turn and this is the right turn. You have to take left turn with respect to the body of the aeroplane only, not with respect to the observer position. It's very clear. You have to take the left or right turn of the aeroplane always with respect to the body of the vehicle. Now left turn means it is like this. So now it is, left means it is moving like this. Left means it is moving like this. Right means it is moving the other way. So this is the direction. You have to take that left turn, it is with respect to, I am indicated it is a left turn, that is L by T, left turn, it is negotiating a left turn. And in doing so, it completes 1/4 of the circle, of course, 80 meters radius of curvature. Here, R value is given, that is 80 meters. And once you know the velocity in meters per second and the radius of curvature, that is 80 meters, you can calculate the precessional velocity. It's called omega of subscript P, precessional velocity. It is V by R. So this value is 83.33 divided by 80. This gives you 1.04 radians per second. The precessional velocity of this particular vehicle about a center, about a vertical axis, it's taking 1.04 radians per second. Precessional velocity you have calculated. The mass of the engine and other parts is given, that is M is given, that is 520 kgs, and radius of curvature, radius of gyration is also given, that is so representation is small k, it is 345 in meters, it is 0.345 meters. So that you can calculate the mass moment of inertia, that is I is equals to mk square. The formula is I is equals to mk square, that is 520 into 0.345 whole square. This gives you the moment of inertia, that is it is 61.9 kg meter square. The units are kg meter square. This is the mass moment of inertia of the engine and other parts. And of course, it is running. The angular velocity of the engine is also given, that is omega. N value is given, N is equals to, it is 2400 rpm, and you can calculate omega, the velocity, it is 2 pi n by 60, that is 2 pi n is 2400 divided by 60. So this you are going to get 6 4s and it is 80 pi. So this value is 80 pi. You got that it is the velocity is 80 pi omega. Now let us make use of the formula for the gyroscopic couple. I am writing GC is equals to, gyroscopic couple is equals to I into omega p, where I is the mass moment of inertia and omega is the angular velocity of the engine, and omega p is the precessional velocity of the engine or precessional velocity of the aeroplane. And you can substitute all the values is known. I is equals to 61.9 into, you have omega, you got it is 80 pi, and omega precessional velocity you got it is 1.04. If you multiply all this, you are going to get it is 16.18 kilonewton meters. The units are kilonewton meters. This is the magnitude of the gyroscopic couple. You got the magnitude, and this much couple is acting on the vehicle. Now let us draw the angular momentum vector, and with respect to that you will be understanding how it is going to affect the stability of the aeroplane. Now let us it is very clearly given, the observer is at a rear end. See that, seen from the rear end. So this is tail or rear end of the aeroplane. So this is the direction of the view. Direction of view is given. So the observer is at the tail end, and with respect to the observer, the engine is said to be, it's rotating clockwise. It's rotating clockwise. The engine, now I am the observer and I am at rear end, that is a tail, and with respect to me, the engine is rotating clockwise. Now you will be using a right hand screw rule. Your right hand screw rule, the folded fingers indicate the direction of the rotation, the thumb indicates the vector direction. So let us draw the vector. That the initial vector is let us draw, it is OX, that is angular momentum vector. It is drawn to the right because you are applying the right hand screw rule. Your direction of the rotation of the engine, it's clearly mentioned, it is clockwise. With respect to the observer, the engine direction is always with respect to the observer only. You have to make a note that turning is with respect to the vehicle and engine is with respect to the observer. These two things are very important in solving the problems, and draw the angular momentum vector with respect to this particular notation. Keep your right hand folded fingers in the direction of the rotation, and the thumb gives that this is the direction of the thumb. And as it clearly mentioned that you are negotiating a left turn. Left turn means the angular momentum vector is shifted to the left. Here this is the direction and it is shifted left, so it moves up. So let us draw the other position, that is x prime position. This is what is active gyroscopic couple. You have changed the position to the left, but reactive gyroscopic couple exactly opposite, that is x prime. X is the reactive gyroscopic couple, this is RGC. And to understand the effect of this couple, the magnitude already you have calculated. Keep your again right hand, the arrowhead in the direction of the arrowhead, and folded fingers transfer it upon to the body of the vehicle. Here you got that effect is the folded fingers indicate that nose is raised and the tail is depressed. Now you can just understand that. Keep your right hand again in the direction of the RGC and transfer it upon to the vehicle, that is aeroplane, and folded fingers indicates the couple in which direction it is acting, and the effect is nose is raised, tail is depressed. Now you can conclude that effect is the tail is you can write down the effect of gyroscopic couple is your nose raised and tail depressed. You can conclude that effect of the gyroscopic. These two are important. The magnitude of the couple is one part, and the effect of the gyroscopic couple which affect the stability of the vehicle. That means when you are negotiating a left turn, the nose of the vehicle, that means as it goes to the left turn, the nose will be raised. Practically also you can observe that when it negotiates, it's going to raise the nose, and so that the pilot can be controlled the vehicle, aeroplane. I hope that you have understood the problem very clearly. There are two parts separately. Schematic diagram of the application aeroplane. I have done the top view, and after that I have switched over to the given data and the calculation part of it, and I have calculated the gyroscopic couple. And after calculating the magnitude of the gyroscopic couple, how it is going to be affected, that can be understood very clearly by drawing the angular momentum vector. So this gives you the effect of the gyroscopic couple, how it is going to affect the stability of the aeroplane, and it can be understood very clearly. Thank you very much for watching this video.